Hello, everybody. My name is Yuri. I work at PVS-Studio. I'll tell you more details about me later if you're interested. And today we are going to talk about a type system of a static analyzer for C++. So here's me. I'm working at PVS-Studio for, well, about 3 years now. And I'm kind of deep inside the C++ static analyzer code. So I decided why not to tell you about some of its internal things that happen inside. Okay, so what are we going to look at today is what this thing actually is, because some people, I think, don't really know or haven't tried anything like a static analyzer before. So what it has inside. One specific aspect about it is how types of C and C++ languages are represented internally. And that is because, spoiler, we are currently rebuilding our type system because the old one was kind of painful to use. I'll tell you about this also. But first, what is a static analyzer, and how do we define what is it? So to do that, we need to look at compilers, really. It may be surprising for someone, maybe not, but compilers and static analyzers are actually tools from the same category, kind of. So what does your typical compiler have? Well, it has something called front end. This is where your code comes in from the source, and this is where the syntax analysis is being performed, semantics are figured out, and the compiler deals with types, because we are working with a strongly typed language, which is types are important. So after the front end has done its thing, it produces intermediate representation. Different compilers can use different formats for that, but the idea is the same. It's common to do. This goes to the so-called middle end, which I don't really like this term because it's middle, but anyway, it's called middle end for some reason. Optimizations happen there. The code in the middle takes the output from the front end and performs some platform-independent optimizations. And then it goes with the IR again, which finally gets into the backend. And there, what happens is the compiler performs platform-specific optimizations, and it produces your assembly code, basically, which is then assembled, and you get your executable or library or whatever you're compiling. Well, it's not that simple, of course. I know linker is involved, and here an object file is actually generated, but that's not the point here. You get a binary. So why they have this structure is because if you want to create a compiler for a different language or for a different platform, you can swap a different front end and back end in, and it will work with the man in the middle, optimizing everything. So great. So why am I talking about a compiler when I'm talking about static analyzer? If you look at a static analyzer structure, you will see something kind of similar, but different. So it does have the same kind of front-end component as the compiler does. Basically, they shouldn't even differ that much. For example, Clang has a static analyzer, and they just use the compiler front end and then perform their checks on the code. And instead of all that good stuff you saw on the previous slide, the analyzer doesn't really have code generations or optimizations. Instead, it has diagnostics. And here it checks if your code has errors. Those are similar to compiler warnings, but since it's a specialized tool, it can afford to be more comprehensive, to perform more checks, and to go more in depth about its checks than a compiler can. And why those are similar to compiler warnings and not errors? Well, because the code a static analyzer has as input, the assumption is that code is compilable. So it should be valid. If you pass it something which is not compilable really, like there are syntax errors there, you will get probably something weird in your output. So here you go. Here is the simplified scheme of static analyzer. Once again, we have the front end. The compiler has all this cool stuff and produces code. Static analyzers have this stuff, and they produce a log with messages about some problems they find in your code. And as you can see, front end here is the point of divergence. This is the similar thing between the tools, and that thing is in gray at the right. It's where they go different paths. Oh, okay. So I hope you kind of understand the difference and the similarity between compilers and analyzers now. So let's go back to the topic, actually, back to types. So as I said, I work with C++. Well, C and C++ because one module works with both languages in our tool. So let's see really briefly in a simplified manner what our languages have in terms of types. Well, we have plenty. So we've got built-ins, we've got derived types, and we've got user-defined types. Built-ins are basically, you can divide them into integral, which are ints and also characters, and also booleans. A floating point, obviously it's floating numbers like float and double. A void is also a type. It's also a built-in type, and it's kind of special. You got a null pointer t here, and that's basically it for built-ins. They are a primitive numeric types and stuff like that. Now, what's a derived type? Well, we've got pointers here. We've got arrays, which are actually pointers in disguise. We've got references. They really want to be pointers, I think, but they fail kind of at it because they are safe. And we've got functions, which also boil down to pointers in the end. So derived types basically are just for indirection and dealing with addresses and stuff like that. And user-defined types, in principle, the simplest one of those, because you've got structures, classes, unions, and enumerations here. In principle, this is simple. You just go and define your own type, but in practice, they are probably the most difficult part to deal with. And all those types, they are interconnected. So they use each other a lot. By the way, templates are not here because I just decided not to overload this structure. Just keep it simple. Okay. Now, let's say you want to create your own compiler or a static analyzer or whatever. Something that deals with your language of choice. How do you represent types used in your language if your language is typed, which C++ is, obviously? Well, you've got some options here. The first option is, let's say you have a declaration like that. It's a pointer to a const integer, and it's colored like that because of a reason. Well, what's the reason? Well, we are going to divide it in parts. So this little star there is a pointer, so we represent it as some kind of tag which indicates, okay, we've got a pointer here. Now, we have a pointer to int, but not just any int, it's a constant. So we put const next, and the type itself, the underlying type, goes last. So if you read it kind of letter by letter, you go pointer to constant. That makes sense. Why are there 4 slots here? Well, because it's a string. So this way of representing types involves encoding them as strings. And that is what we are currently using. And this is what we don't like to be using. So a new system has to be born. And this is why I came here, basically. The second way, the new system, which is to be born, what is it? Well, remember that previous slide. You just implement the type hierarchy in the way it's represented inside the language itself, inside this scheme of type relations and kinds of them. So yeah, both those approaches may have advantages and disadvantages, but I hope I will show you that the encoding approach is not the ideal one, let's say. Let's say it like that. So what are pros and cons of encoding your types as strings inside your front end? Well, one advantage I can clearly see here is strings are contiguous in memory. So you will have a system which is very, very cache friendly. Well, at least if you are within the same string. So while you are iterating through characters, your CPU is thankful to you because it can use its cache efficiently. And well, the second advantage is I don't really know. Because strings are not really convenient to deal with in general. And using them to represent something complex, such as types, probably not ideal approach. So minuses of that, this goes slow, and slow kind of contradicts better locality and cache friendliness, but if you think about it, when you're working on one string, it's all good. When you switch to a different string, which is somewhere in the memory, you're probably hitting a cache miss at this point. So dealing with multiple strings is not that cache local as it seems. Also, algorithms of working with strings to get specific parts of them and to analyze them can be really inefficient. And we saw this in many places, like you get a slowdown because someone used the type information. And then you go and fix it to use it in a different way, and your slowdown disappears, and the slowdowns were significant. Anyway, you might want and or have to iterate through the same string over and over in different parts of your code. And yeah, like I said before, at the beginning of this slide, it's like a really inefficient to work with strings, especially in C++, especially if you don't use the standard library extensively. It's gotten better these days, but still. Okay, there's one little problem with encoding is that here are some screenshots from our header file which defines the encoding class. And we are running out of letters. There are so many options and so many ways to write code these days, and we have to deal with two languages, so we are kind of running out of letters here. Like, why is Z why Z is null pointer? Well, I don't know, because Z was free, because N was taken. So yeah, this gets messy very quickly. And there's another tiny issue. As I showed you earlier, let's take a look at some declarations and try to figure out their types. So, int pointer. Well, this one should be easy enough, right? So it's just pi, pointer to int. Okay. This one is a little bit more complicated. So it becomes my class, and that little weird character there you see at the beginning, it represents the length. So you put length of the substring which comes next there. Oh, I've got a question. So do analyzers like PVS treat type aliases as different than their C++ type and alert on unreasonable conversions? No, they don't. Type defs are resolved into their original types. Okay, back on track. So the next declaration. How would you encode that? Well, it's going to be this monstrosity. So it's like a function which accepts an int and then a pointer to const char, and it returns an int. See what I mean when I say it is inconvenient. Okay, and the example which is going to be, I think, really tough to figure out. I know the answer, but I stole it from the debug view of our analyzer. So it's going to be that it combines class names, namespace names. The little q at the front means that it's a qualified name with namespace, and the T just before the array means it's a template. Next, you have the element type, and the big number at the end is a hash value of a non-type template parameter, the 10. This is not the real value, by the way. It's I just made it up. The real one was a little bit longer. Okay, those are really tiny issues. The big problem comes when you are starting to work with that system. So let's say we've got some function and we only accept function types like that. So we do a check here. I call it a quick bug out check. So it is supposed to be a quick way to just bug out if we are getting some data we don't want. Or is it so? Is it a quick check really in this scenario? Well, let's see. Well, here is code from our code base. From that type-info member is function, which is supposed to produce a quick exit if we don't have a function. And now a question here is how many loops do we see in this code? Well, I think if we don't consider that operators might be overloaded, I think we see like two possible sources of loops or really slow code. We've got two functions called here. Skip CVDE is not really interesting. It simply skips qualifiers of assigned to a type. Normalize is, well, frankly, I hate it. Why do I hate it? Because we'll see right now why. So this normalize function, by the way, returning to the question we've got earlier, this is what normalize is for. A part of its job is to check if a type is const volatile qualified and deal with it. It resolves type defs and boils them down to their original types that they were produced from. It tries to figure out template arguments. It's not always successful. And if you have a class, there is a special object for that, a special type of entity which contains extended information about that class. And the normalize method is supposed to retrieve that for you. So qualifiers just goes over the string and sees if some letters are what it expects to see, and then it caches them internally inside type information in special bool fields for const, volatile, and so on. Resolve type defs checks symbol tables. Templates are just dark magic. They are outside of scope of today's talk. So we don't want to deal with them in encodings. And this class info thing, it goes to a symbol table and fetches the information you want. Okay, so this is clearly a loop. This one is, well, kind of it should be something really fast right now. Well, not really. often leads to recursion because it may have to recurse here to normalize again. This one is recursion because templates. Well, really because they also need to figure out type defs and stuff. And this one also, in many cases, needs to deal with type defs. You may have a template class and it becomes a mess here. Okay, so why am I telling you this? Because that's why. You want to check something and see if it's a function or a pointer or whatever, or class. Why do you need to go through all this? Why do you need to jump into different symbol tables and deal with strings and so on? Yeah, so that's why we decided that we don't want that old system with encodings anymore, and we are going to make a better one, which we did. So a better system, what should it look like? Well, types are kind of a hierarchical set of things in a language. They depend on each other. They have different kinds of relations. So it's like a graph or a hierarchy tree similar to that. So here's the brilliant idea, right? Let's take a hierarchical set of things and represent them as a class hierarchy. So yeah, why had no one thought about that before? Well, actually, Clan did. And here I'm just going to take a small pause and I will say how awesome people who made Clan are. It's a great compiler, I love it, and more importantly, it inspired us to finally rebuild our type system. And I borrowed a couple of ideas from there, so thank you, Dragon, you're awesome. Okay, now, so we are going to represent each type as a class. And there's going to be a hierarchy of those classes. So we've got the base class called type, which has an ID. ID refers to some category of types. So as you can see here, built-ins are all in the same group. Pointers, references, functions, and so on, they may be like their own group with their own ID, or they may be a part of some bigger one. Here's what's very important. That's a canonical type. I'll tell you about it, why we have it, and why we need it a little bit later. It's a canonical representation of a type. Now, of course, it has derived classes, and they hold specific info. They all inherit from type, but they are kind of different. But anyway, let's first, before we talk about the class hierarchy and the class parts in more detail, let's see the same thing as before. We've got some type, and we want to get out of here if it's not a function. And again, the same question, is this or is it not a quick bug out check? Well, to understand how it will work in the new system, let's see what this isA method does. It's a template. It gets a bunch of type IDs. You can pass it multiple and checks if your type, its internal ID, is one of those. So that's why we are carrying around this ID thing. And just to make sure we see everything here, the ID is just an enum. It's a basically unsigned char, uint 8. So far, it's more than sufficient to um, represent every type in the system. Okay, so the check by using the ID is much more simple. But the ID is not the killer feature here, of course. Let's go to Canonical and see what it does. Well, essentially, canonical type is, again, returning to that question I answered earlier. Canonical type is the type from which any type defs were derived. So if you get a type def, you can always get the source, the initial type from it by using that canonical thing. Well, let's see at this variable here and try to figure out what its type is going to be and what its canonical type is going to be. Well, for a simple case like that, it's a built-in, and specifically it's an int. And its canonical type is exactly the same. It doesn't make any difference for declarations like that. Now to type defs. So we've got something like that. Its type of A will be alias type def. This information is important for us to know because we also can check aliases for incorrect usage and something like that. We are not just interested in the source type by itself. We want to know the context, so we keep information that it's an alias, and its canonical will be again built-in int, because this is what your type def here resolves into. Okay, let's take a look at a more complex example. Well, let's say you've got a type def and you've got a using on that type def, and finally you've got somewhere in your code the variable a again, like in the previous examples. So what does it have as its type and all other stuff? So type of it is obviously an alias, because we've got the using the ultimate int of doom there. And we know that under the hood, this alias is actually an int. So canonical will still be int. No matter how long the alias chain, we also always know the source type, that the underlying type from which the type defs were made. And this improves things greatly as compared to encodings, because when you use encodings, you are dealing with names. You're not working with classes. And to convert that name into something meaningful, you have to go and look it up in different parts of your lookup tables, also in caches and stuff like that. This one is a really fast constant time way to get you the type from which all those aliases were made. Okay, and also we are interested usually in the entire alias chain. So there's a way to unroll it, and that is what source is for. So for our ultimate int of doom, which is using, the source is going to be a type def myInt. And you can use that source. It's also a type. You can use its source and so on and so forth. You can walk those alias chains quite easily. So those are the basic parts of the base type. Really, it has an ID and it stores its canonical representations inside it. Okay, let's look at the structure of what we've got. So type at the center is of course the base class, and every other kind of type in the system is derived from it. So we've got built-ins, we've got complex from C, because we are dealing with C. We've got pointers. Okay, pointers can be just pointers, or they can be member pointers. So a member pointer is derived from pointer. We've got arrays. They are not derived from pointers, but I will show you how we can convert them really easily into pointers. References, which can be R-value, L-value references, forwarding references. Classes, class members. Class members are types of their own because you need to somehow associate that, for example, like int for a class field with the class itself to know the relation between them. Okay, enums are kind of easy. Aliases, this is what we kind of briefly looked at. Functions, and now what kinds of functions we may have in our program? Well, we can have just plain functions. We can have constructors. We can have destructors. We can have various kinds of operators. And of these various kinds of operators, assign operator kind of stands out because it's a special member function of a class. Also, another member function usually of a class is a cast operator. If you want to convert your type to a different type, you can declare that. It's not really an operator. I just call it that because the keyword used for it in C++ is the same. Okay, now it's a small part of what we're dealing with. We can also have auto, and it sees, I think, increasing usage these days. And we've got decal type, which is a different kind of auto. We've got, of course, templates. Template variables are their own kind of entity. They use roughly similar machinery to templates, but really it's just a wrapper around a declaration. Template parameters, template specializations, which we can track and access through a special table, again, with an easy and quick way to access it via the primary template type. We've got types after some conversions. This is also what Clang calls them. Adjusted types can be of different kinds. They can be deduced from auto. They can be decayed when you, for example, pass an array to a function as a parameter. They can be substituted template args. they can also be parameter parks, and they can be template instances. So here's what the hierarchy of types looks like. It's not really deep, um, but it's kind of vast. Okay, so that's all good and fine. We've got an ID, we've got canonical type, but I think we forgot about some important thing, and that is qualifiers. Like, let's say you've got something like that in your code. How do we represent it when we parse it? Is it something like that? By the way, I don't know why you would write volatile for a constant, but anyway. So if it goes like that, if we deal with qualifiers in that way, if we just make an ID, it's going to be pointless, right? The idea was to simplify the system and make it more convenient. So that's not the way we are going. And here's the for qualifiers, here's the idea, which Clan was really helpful. So again, thank you, Dragon. To represent qualifiers like constant volatile of some variable of some type, we use something called qual type. And what is it? Well, basically it's a pointer, but not really a pointer. So what a pointer is? The pointer is address in memory, right? So if you are under a 64-bit system, and I asked you what is the size of the pointer, you would probably say 8 bytes, right? And you would be kind of right if you said that, and kind of wrong. Because operating systems, at least the major ones like Windows, Linux, Mac, I'm not sure about Android, but probably too, they divide their execution space, their memory, into kernel space for the operating system and the user space for user applications for us to run our code in. And the pointer size in kernel space uses all 8 bytes to address memory. But in user space, you get only 7. Well, 64-bit. If we are talking 64-bit systems here. In user space, you have only 7 bytes to address something in the memory, and that 8th byte, it's zeroed out. This part is reserved, and it's always 0 in user space. I heard that CPUs there's a proposed optimization for CPUs. If you are coming from the user space and you've got something other than zeros in this 8th byte, you can still kind of dereference a pointer, but the CPU will remove and ignore this byte for you. But it's not, of course, yet implemented anywhere. It's just an interesting proposal I heard about. Okay, so that's kind of a waste. So we are going to really make it not waste to our byte here. So we take this byte and we put our qualifiers const volatile restrict as for C. So we just put bits inside that byte, put the address of the type in the 7 bits we've got for that, and we carry the pointer around. And when we need to dereference it, it's a class, it has the arrow operator, everything works fine. If we need to check qualifiers, we can also ask the pointer kind of itself. And we still got 5 bits here for our needs. Clang stores more information in their qual type. And yeah, we don't need all that information Clang uses, so 5 bits kind of free for us. A question: does your type system know how to navigate and reason about various callable types, overload sets, etc.? Um, the old one has difficulties with that. It needs to rely heavily on lookup mechanisms external to the type system, really. Um, this one will be able to find overloads reasonably well. All right, so we are running out of time here, I think. So call type, again, it's 8 bytes in memory, and those 8 bytes pack inside them type qualifiers and a pointer to the base class. It's kind of a simple concept. Okay, now how it fits together. We've got the type system object, which manages all the types. It's singleton. There's only one of those in the system. So when you want to create a type, you don't just create the class. You go to it and ask it to make one. It has a factory. Well, why it has a factory? Because it caches types. Our types also exist in just one single instance of each one. It does make sense to make multiple ints. So if you ask it to give you some type that has previously been created, it will just look up in the cache and give it to you. It won't create an object. Well, it has a hasher and it has type traits. Just in a moment, we'll talk about it in more detail. Okay, at the current stage, at this point, what's the good thing about it? Types we create are immutable. You can only read them. You can't in any way corrupt them, which is not true with string representations, really. Each unique type only exists in one copy. Types are hashed. The factory hashes whatever you give it as input, as parameters, and it associates this unique hash with the type it's going to create. So to compare types, you can simply compare their hash values, which is really fast. Qual types are kind of pointers. They are not nullable, so there's no way to go wrong about using them. You can dereference them left and right. You don't have to check them for anything. Okay, so looks good. All right, we are going to be quick here because we've got 10 minutes left. Let's look at the base class for types. What it contains, the interface of it. Well, it has the ID, which I was talking about, this ID. It also has a couple of service methods which check things about it. So unresolved is kind of a null for type. Auto is a quick way just to check if it's any decal type, auto, and similar type. Okay, we get the method which just returns canonical, which is stored here. We can create a call type with the specified qualifiers from this type. It's a convenience feature because I was tired of writing call type constructors everywhere. And it has size of, align of methods. They look up a hard-coded kind of platform-specific set of sizes and alignments for different types, and it has a hash. That's it. That's basically the entire interface of the base class, and it's sufficient to work with any type really. And just for a change, let's look at some derived class from that base. Let's look at the pointer. So what can we do with a pointer? Well, we can dereference it, and that dereference method returns a call type to the underlying type pointed to inside the pointer class. And you can also, kind of a convenience feature, you can check what is under the pointer with a kind of this template function. You supply it again IDs, and it checks for you if the pointee type is some of those. Okay. So we've got a type structure. Do we have a polymorphic type structure? Well, no, not really. We decided against it because virtual functions are nice, but polymorphism is nice, but it can be slow and it may clutter your base class. The kind of distinction between bases and derived types are made in a different way. So let's say we've got a function which checks if we have an int pointer. It gets a call type. So you can ask the call type to return you pointer to a pointer type. If it's not a pointer type, it will get you null pointer, which at this point you just get away from here. So we dereference it. We again try it as a built-in type, and we check if it's an int. So the important thing is that try get as function here. So let's take a quick look at it. What it does, it just calls that. Get type PTR is a member of call type. And what that does, it checks the type ID and casts it, if it can, to the requested type. That's kind of a dynamic cast, but static, if it makes sense. And the important part here is that this is a template specialization for every specific derived class from type, which, yeah, I used a macro here, but anyway, there are two of them. You can convert IDs to types and back at compile time, kind of easily. Okay, so a different way that we could write a function which checks if this is an int pointer is using traits. So I'll go kind of faster here. Yeah, so you can use traits. And what are traits? Well, if you, probably every one of you saw these guys in the standard library, they are really handy to deal with various type operations, and we've got them all. Yes, even is convertible and stuff like that. This is just a small representation of what of the big picture. Traits allow us really to mimic what you write in your C++ code. If the parser detects, for example, I don't know, is integral v call in the in some using or some template or something, it knows where to go and what to call, what to do with the type. Right. And we are near the end here. Just let's look at one trait. Decay. How decay works? Well, first we remove all qualifiers and strip it of a reference. Then uh, functions become pointers to functions. So we just add a pointer to function. Arrays become pointers to their elements. Um, this works fast and simple because those calls, they deal just with a little bit of bit manipulation and passing pointers around. They don't traverse any strings or they don't allocate really any memory. In the best case scenario, if you don't have to create new type for int, for example. Okay. And now together, how it's going to work when we finish conversion from the old system to the new one. You get, let's say, code like this as an input to your system. The parser looks at it and it creates a tree node for declaration because it's a declaration. And it also, at this point, will figure out the type of the variable being declared. And this type goes into the declaration. So you can ask the declaration to give you the qual type of the types it belongs to. And then at some point, this declaration might get into a diagnostic rule, and the diagnostic rule will use those trait mechanics to kind of check. If you're curious about how types are assigned right now in the old system to nodes, it's a pain. The parser defers this to a later stage of translation, so-called translation stage, which has a built syntax tree, and it just goes around it figuring out types. Okay, so that's basically the end of that. What I wanted to say is I hope it makes sense what I said here, because it's a vast topic. I could talk about it for hours, as you probably have noticed, because we ran out of time actually a little bit. But yeah, that's an intro. If it's useful, maybe I'll make kind of different kinds of talks about different internal mechanisms in the future. So yeah, that's it. Thanks everyone for listening. Sorry for being so verbose as usual. And yeah, if there are any questions, if we have time, I can answer them. I guess there are no questions. Okay, so we are done. Have a good lunch. And I hope you at least found something useful for you or learned something new.